just want to remind everyone that currently really the only method of integration that we know about is U substitution, right? So either if we're integrating something, it's either we have to do a U sub or we have to simplify it or recognize it as some sort of thing. I was helping someone with a problem earlier today in office hours, and we got to the place where we were having to integrate, I don't know what the limits of integration were. We were having to integrate 1 over the square root of 1 minus 6y squared, I think, dy. It might have been with x's, I don't remember. But then we have to recognize, oh, this is an arc sine kind of thing, right? And I would have to do more work to actually do this integral, but I know there's something with an arc sine of probably y over root 6 or something. I don't know exactly, but I know we can figure it out. So again, everything at this juncture is still going to be either a U sub or you have to simplify the integral in some way so that you can actually anti-differentiate it. All right, so let's get going. So we're talking about some volumes for a bit. And we've got all the methods. We've got slices. We've got annoying things on my computer. We've got disk. We've got shell. We've got wash. Disk and wash are the same. But let's look at some slices. I don't think you're going to see too much in the way of slice examples, but you'll probably see some. So we should probably take a look at least a couple. So here's one that I just came up with. It's probably, the numbers are probably not going to be super nice. It is often true when you're dealing with finding any sort of area or volume or arc length. A lot of times the numbers just aren't going to be nice. That is mostly always going to be the case. Unless someone has really, really tried hard to make the numbers nice. I will say, especially in web work, the numbers are probably going to be extra not nice because no one is working hard to make them nice. The computer is just generating things that at least work. So yeah, the problems you're doing for your homework are probably going to be mostly nasty. So let's look at this setup. And I didn't write the words out because they take so long to write out. But here's the idea. So we have a region, and this region is bounded by the curves y equal to 9 minus x squared and y equal to 0, also known as the x-axis. And our job is to take, so the way they usually write this is we're going to take cross sections perpendicular. I'm just going to use that symbol for perpendicular. Cross sections perpendicular to the y-axis are squares whose side length, well, is this. I should just say our squares. Right, so I take a cross section perpendicular to the y-axis. I'm still using, I should say our squares with base length that is the, I guess, the width of the enclosed region. There's probably a better way of writing that. Okay. So the idea is you're taking this length, right? So here's my cross section, or my, really, I'm not drawing it here, although I could. We're imagining, right, like what they're drawn over there, right? A square coming out of this. Think of it as some volume. And so right, my cross section that I'm taking that is perpendicular to the y-axis, right? It's parallel to the x-axis, perpendicular to the y-axis. That cross section is a square with a base that's given by the width of this region. Okay, so we want to find the volume of this shape. All right, well, so we don't have to draw any of these pictures, but it's nice too. So I'm imagining my shape looking like this, right? I've got my parabola here in the XY plane that's kind of flat. And I see that the cross, right, this is supposed to be the same as this here. That little rectangle is giving me a square. I guess a square with some thickness. So the volume of this slice, which I've already written over there, well, yeah. So the volume of that slice is just the area of the square, which is the length of a side squared, times the thickness, which is dy. We know it's a dy thickness because the thickness or the width of that rectangle is a small change in y. We also know because it's horizontal, which means we're going to have to find the length of this in terms of y. So I need to solve this function y equals 9 minus x squared for x in terms of y. If I do that, I get positive x squared equal to 9 minus y. I get x equal to not just the square root of 9 minus y, but plus or minus the square root of 9 minus y. So what's really happening here, and this happens quite a bit, is that this right side, where x is positive, because we're on the right side of the y-axis, is x equal to positive square root of 9 minus y. And this left side is x equal to the negative square root of 9 minus y. And so the length of this strip I've drawn is the right side minus the left side, which is the positive square root of 9 minus y, minus the negative square root of 9 minus y, which is 2 times the square root of 9 minus y. So that's what's going to be the length of one of the sides of this square. So then the volume of this particular slice is going to be that 2 square roots of 9 minus y quantity squared dy, which we can totally simplify. 2 squared is 4, square root of 9 minus y squared is 9 minus y. Great, that's the volume of that slice. And now, like we've been doing, we're going to add up all the slices by integrating. So our slices go as far left as the bottom of the region, which is the x-axis, right? So if you think about it, our slices are, or you can either think about either the strips going down to x equals 0 and up all the way to whatever that point is there, it's 9. Or you can think about them in this picture, going all the way down to the x-axis and going all the way up to, again, that point there is the point x is 0, y is 9. So we're going to add up all the slices from y equals 0 to y equals 9. I'm going to erase this now because I'm out of room. So the volume here, the total volume, is going to be the integral, or the adding up from 0 to 9 of all the areas of the volumes of the slices, which is that amount, 4 times 9 minus y dy. You can distribute the 4, but I don't really want to. I'm just going to leave the 4 out in front and integrate 9 minus y as 9y minus y squared over 2. Maybe it would have been good to have the 4. I don't know. It's fine. From 0 to 9, you plug the limits of integration. You get 4 times 9 times 9 is 81, minus 9 squared over 2 is also 81 over 2. And then you plug in the zeros and you do get 0. So we end up with, so here's the thing that actually comes up kind of a lot when you're dealing with areas and volumes and all kinds of stuff and work. You often get this thing where you plug in some numbers and you get something squared minus half of the same something squared. When you take a number and you subtract half of it, you're left with the other half of it. So this should be 4 times 81 over 2. You can either factor out an 81 and say, oh yeah, it's 81 times 1 minus a half, or you could get the common dollar, say this is 162 over 2 minus 81 over 2 is 81 over 2. But really it's easiest to be like, oh yeah, I took a thing, I took off half of it, I'm left with half of it. And then cancel a 2 here and a 2 here, and you're left with 162. 162 cubic units of whatever, right? It could be cubic feet, it could be cubic inches, whatever, or it could just be 162 cubic units of volume. So interesting question. What happens if we change the shape? Meaning, what if it's the same region, but now instead of my slices or my cross sections being squares that are perpendicular to the y-axis, what if they're semicircles? So what if we took the same region? I'm going to try and actually draw. I'm going to do the last one, but I had time to draw it. So I'm going to draw my XY plane again. Here's X, here's Y. Here's the region. All right, that's my parabolic region. That's the point 0, 9. There's the point 3, 0. There's the point negative 3, 0. By the way, we usually label this in a way, when you label the axes, you're labeling the positive x-axis and the positive y-axis is typically the standard way to label them. And now instead of having squares popping out from my length there, I'm going to have semicircles popping out. So this is going to give me a semicircle. Hopefully you can see this picture all right, because I'm doing an excellent job of drawing it, if I just say so myself. I'm actually doing a better than usual job, I gotta say. My picture is turning out pretty good. Kind of looks like a taco, except a very, very narrow taco, not a taco you want to eat, right? Because there's not room for all the good stuff. It's very thin. It's like one of those, like, I've actually never had one of these, but you ever seen those ice cream tacos they sell, like in the frozen section? They're like ice cream and chocolate, and they're like super flat. So that's kind of reminding me of. Anyway. Hard shell taco, not what I want. I want a soft taco. I'm not hungry. I just ate lunch. Well, it's like a taco to me. Okay, anyway. So, what's the volume? You guys are like, why is he talking about tacos all the time? Tacos are delicious. So, the volume of this slice. So, we can still use the same information we had before. The length of this, right? This thing here, the length of that strip is still 2 square roots of 9 minus y squared. The difference is here, I'm not trying to find the volume of a square. I'm trying to find the volume of a semicircle, I should say a semicircle with some thickness, whose radius, well, the radius of this circle or semicircle is half the length. That's actually going to come out pretty nice. It's going to be just half of this, which is just the square root of 9 minus y squared. So the volume of that, well, the area, it's area times the thickness. The thickness is just dy or d whatever you happen to be using in the problem. And the area is the area of a semicircle. And we know the area of a semicircle is half the area of a circle. So it's literally going to be 1/2 pi r squared times dy. Where the radius here, excuse me, is this radius here, right? It's this from here to here. That's our radius. So that's going to be the square root of 9 minus y squared. So I'm going to get 1/2 pi times the square root of 9 minus y squared dy. That's going to work out real nice. So then once again, we quote unquote add up all these circles, semicircles. We add up all the slices, what I should really say, to get the total volume as the integral still from 0 to 9 of, I'm going to put the 1/2 pi out in the front because why not? That squared is just 9 minus y squared. I feel like, I'm trying to think, like, did I make an error on the previous one? Oh, I did. I made a mistake in the previous problem. I'll fix it in a minute. Let's finish this one first. Yeah, I totally did make a mistake. Sorry about that. If you guys think you see a mistake, let me know. So, yeah, right, because this function is definitely, now I'm like doubting myself. Let me double check. No, I didn't make a mistake. I'm just crazy. My problem, I know this. My problem is I'm thinking of the equation of a circle, which is not what I have here, right? This is a problem. So I also have a circle I'm dealing with. Sorry, did make a mistake. Everything's okay. This is totally right? I solved for x appropriately. Yes, I did. So yes, it is still, it's just that I wrote this wrong here. This was not this before, it was that. Sorry. Hopefully everyone's okay with that. Okay, now we are actually there. We integrate this. 1/2 pi times 9y minus y squared over 2 from 0 to 9. Again, we're going to see that when we plug in 9, we get 81 minus half of 81. When you plug in 0, you get 0 minus 0. So we end up with 1/2 pi times 81 minus half of 81 is half of 81. So here I get 81 times pi over 4. That's my volume. Questions about either of these examples? Would you like to see one more slice example, or should we move on? What does the V say? That says this one here? That says V total. Yes, I know I wrote it terribly, so thank you for clarifying. I usually try and do the volume of my slice in one color, and then the total volume in a different color. And the difference should always be that whatever the volume of your slice is just some equation, whereas the total volume should be the integral of that volume slice. And that's true whether you're not talking about volume by slices or whether you're talking about the washer method, right? You're still using slices that are washers when you're talking about the washer method. Excuse me. No. Okay, let's do one more. Ooh, we can make it a little challenging if you guys want. Or not. I'm gonna make it a little, well, actually, I definitely saw, no, I guess I didn't. I think I saw, but I didn't really. One more. Let's say we've got the base of a solid is a circle with radius 4. Base is a solid, base is a circle with radius 4. And, sorry, find the volume of the solid if cross-section is taken perpendicular to the base R. So, and here they're not specifying the x or the y-axis because the circle has symmetry about both, so it doesn't really matter. So, okay, sorry. Volume, find the volume of the solid if cross-section is taken perpendicular to the base. R. You can make it easy and say they're squares. You can make it a little less easy and say they're isosceles triangles, but I'm going to say, make it really hard to make it are equilateral triangles. And although you don't have to draw a picture, I do think it is really helpful to draw a picture. And I kind of like, I think it's, you really only need the 2D picture. The 3D picture, which is hard to draw, we don't always have to have. So here's what I'm going to do. I'm going to draw my base is a circle with radius 4. So, and then the equation of a circle with radius 4 set at the origin. You could center it anywhere you wanted. Typically, it makes sense to center things at the origin. This is a really, really good reason not to. The equation of that circle is x squared plus y squared equals 16. And since it's not going to matter if I do my cross sections horizontally or vertically, right? Since either way, we're going to get the same shape. I'm going to do them vertically because if I'm given the choice, I usually like to use a dx instead of a dy. So there's the base of our equilateral triangle. And then what we have happening, I'm going to move this here, is that jutting up out at you is the of the triangle, right? So right, there's this triangle and it's pointing right at you. Except, right, it's coming off here. So this is probably not going to look excellent. I'll try though. I've drawn better. No, I don't know. I guess you don't really need that. So there's an equilateral triangle sticking out at you. It's probably easier to see. Now, here's the thing. I really just want to kind of, what I really want to do when I draw this is I want to take this XY axis that is flat against the board and I want to essentially tilt it, rotate it, so that the y-axis falls back and the negative y-axis pushes out towards you. So what I'm going to do is I'm actually going to rotate. So it's actually going to be oriented differently, right? I'm going to, right, in the past, my y-axis was here, my x-axis is here. I'm kind of rotating this 90 degrees so that my positive x-axis is here, my positive y-axis is back there. Yeah. This is kind of the more standard orientation when you're graphing something in 3 dimensions, but this is also a perfectly fine way of doing it because we're just kind of taking your usual 2-dimensional thing and tilting it. So we're going to tilt it. So here's my x-axis, and here's my tilted y-axis. That looks all right. And here's my semicircle. Let's see if I can make it happen. Sorry, my whole circle. Sure. That is not the best circle I've ever drawn. Forgive me, please. And then we're essentially taking this up and just drawing it like this. So here's what we've got. So hopefully you guys can see that okay. I've got an equilateral triangle. And so here's what I'm going to do. I'm going to write down the volume of this slice. The volume of my slice is, again, in very basic terms, it's the area times the thickness, which in this case is a dx, right? This vertical strip has a thickness that's a small change in x. Okay, so now to find the volume, I'm going to add up, well, I guess I should really find an equation for the area here. But the idea is going to be to find the total volume. I'm just going to integrate. I'm going to add up all the triangles with thickness, their volumes, and I'm going to go from -4 to 4, because that's how far left and how far right either you can think these triangles going or you can think this strip is going. So it's going to be from -4 to 4, the area of the triangle, which we don't know yet, dx. So we do have to find the formula for the area of an equilateral triangle. And even more importantly, you have to find it in terms of the base of it being between the top half of that circle and the bottom half of that circle. So let's deal with the equilateral triangle part first because it's kind of a pain in the ass. Sorry, pain in the butt. I'll probably swear, not at you guys, in front of you guys at some point. Life will go on. People swear. I'm sure you're aware. So I want to find this length here. Oh no, I was going to find, sure. Let's find the area of an equilateral triangle. So here's an equilateral triangle, and let's call the bottom side L. And so the easiest way to do this really is to use some trig, right? Because all the angles are 60 degrees. And so if you want to find the height of this side, you can say, well, if this is L, then each of these is half of L. And I know that tangent of 60 degrees, I call this the height. Tangent, should I use tangent or should I use sine? Let's use sine. It's even nicer. Sine of 60 degrees is the opposite, which is the height, over the hypotenuse, which is L. And so solving for height is equal to L times sine of 60 degrees, and sine of 60 degrees is the square root of 3 over 2. So we can find the area of this triangle. The area is 1/2 base times height. The base is L. The height is L times the square root of 3 over 2. And simplifying this, we get L squared times the square root of 3 over 4. That's the formula for the area of an equilateral triangle. It's one of your side lengths squared times root 3 over 4. Don't memorize that. I mean, you can memorize that formula. I don't recommend memorizing it. I certainly haven't. So then we do need to know what this length L is in terms of x. So I know I erased it, but the equation of the circle is x squared plus y squared equals 16. And so what we're going to do is we're going to solve for y, right? Because we want y as a function of x. The top half is y equal to the positive square root of 16 minus x squared. The bottom half is y equal to the negative square root of 16 minus x squared. And L, the length from the top to the bottom, right? This thing here, get my red pen here. This length here, L, is the top minus the bottom. So the length L is this minus this. You could write it out as the square root of the thing minus the negative square root of the thing. It's twice the square root of the thing, right? You take a square root minus the negative of the same square root, you get 2 times the square root of 16 minus x squared. And then so the area of the equilateral triangle is L squared times root 3 over 4. So it's L squared times root 3 over 4. This ends up being, so 2 squared is 4 times 16 minus x squared times root 3 over 4. 4's cancel, and you get root 3 times 16 minus x squared. And that's what's going to go right here. Root 3 times 16 minus x squared. Okay, I've kind of run out of room. So let's go to the other side. We're going to integrate from negative 4 to 4, root 3 times 16 minus x squared. I would definitely put the root 3 out in front. And I don't need the other side. We can just do it here. I'm kind of done with this picture. So we're going to find the volume by doing the integral from negative 4 to 4 of root 3 times 16 minus x squared dx. And now I'm going to do something you've probably seen someone do at least once already. I'm going to say, well, hey, look. 16 minus x squared is an even function. How do I know it's even? It's an even function because if you plug in negative x for x and you still get the same thing back, it's an even function. And you do, right? If you plug in negative x for x, you still get 16 minus negative x squared, which is 16 minus x squared. And so what I can do is I can, if your limits of integration are from a negative number to the same positive number, you can say, hey, that's going to be double half the integral, right? If it's even, that means it's symmetric on either side of the y-axis. So if you're going from, negative 4 to 4, and you're going to get some words, you're going to get some number when you integrate this. Well, instead of what I'm going to do is I'm going to say, well, instead of integrating from negative 4 to 4 and getting a number, I'm going to integrate from 0 to 4. It's going to give me exactly half of what I would have gotten because I'm literally cutting it in half because there's symmetry. And then I'm going to double that answer just to make the integration easier. Or really, not so much the integration, but the evaluation. Plugging in 4 and 0 is a bit easier than plugging in 4 and negative 4. But if you ever looked in the solutions manual, they definitely do this kind of step and they don't really justify it. That's what they're doing. They're saying, oh, even function. Go from 0 to 4 and double it. So then we get 2 root 3. Integrate this, you get 16x minus x cubed over 3 from 0 to 4. So you get 2 root 3 times, let's see, 16 times 4 is 64, minus 4 cubed is 64 over 3. And then we plug in 0 and you get 0 minus 0. Now I'm going to say something very similar to what I said before. I've got 64 minus 64 thirds. Or a whole thing minus a third of that thing. A whole thing minus a third of that thing is 2/3 of that thing. So you could easily, you could see that, oh, 64 minus 64 thirds is going to be 2/3 of 64. You could also factor out, I really am a fan of factoring out the 64. So I'm going to write it that way so you guys can see it. Really, whatever works for you is fine, as long as it works. So I'm going to write this as, hey, I've got 2 root 3 times, I'm going to pull out the 64, and I'm left with 1 minus 1/3. That's 2/3. So I've got 2/3 of 64. So I've got 2 times root 3 times 64 times 2 over 3. And then I just multiply it out. 2 times 64 is 128. There's another 2 is 256. So 256 root 3 all over 3. And that's how we would handle some problems like that. All right. Let us continue on. What do I got here? I want to see this. Okay. Sure. People asked about some web work problems, so let's take a look at them. Oh, it says use the shell method. Good, awesome. Let me do one thing. So, again, feel free to stop me or interject if you have a question or comment. I'm just here kind of talking to myself, which is fine. I like me. But yeah. All right. Let's. Let me see. I had an example that I wanted to do, but I want to make sure. Okay. Yeah, that seems like a good one. Let's do that. So I want to find the volume of the region. Sorry, the volume of the solid. I hate writing this. Okay, let me just say what I mean instead of having the volume of the solid, of the region bounded by these things. We're all okay. Here's what we're gonna do. We have a region. Bounded by the following functions. Y equals, let's not make it super crazy. Y equals x squared and y equals 3x. That's our region. Looks like this. Boom, yoink, and yoink. I'm not usually a yoink kind of person, but And there's some points of intersection which we can totally find. And we've set these equal to each other. X squared equals 3x. You get x squared minus 3x equals 0. You get x times x minus 3 equals 0. You get the points, not surprisingly, 0, 0, and 3, 9. X is 0 and x is 3. So we're looking at this region here. And I want to find the volume of the solid generated by, volume of solid generated by revolving around either axis. Let's go y-axis first. Okay, so here's the thing. Most of the time, you can use whatever method you want. Sometimes there are reasons you might pick the shell versus the washer method. Really, the question that is going to determine what method you're going to use is which strip is nicer to draw. And when I say which strip is nicer to draw, what I actually really mean is if I draw a vertical strip, is the upper limit and the lower limit of it always going to be the same function? Like, right, if I draw a vertical strip here, is the top function always that function? Yes. Is the bottom function always that function? Yes. Great. That's what I want. I don't want it to be halfway through changing to a different top function or a different bottom function. You could also equally argue for this example that a horizontal strip works just as nicely. For a horizontal strip, the left function is always this function, and the right function is always this function. So there isn't any midway change. So either kind of strip is fine here. But if you find yourself in the situation where you've got something more like, I don't know, a shape that might look like this, where you're looking at this region here, this region I would not want to use a vertical strip because halfway through my vertical strip is going to change from having whatever this line function is on top to whatever this circle looking function is on top. That is undesirable because it means I'm going to have to use two intervals. I would much rather, for this kind of picture, use a horizontal strip. Because a horizontal strip, no matter how high or low it goes, the left function is always this, the right function is always that. So I'm going to say it again because it's important. When you're doing these volume problems or even area problems, you want to try and draw a strip so that no matter how much you slide it, if it's a horizontal strip up and down, or if it's a vertical strip left and right, you're not changing where the ends of your strip are what function they're touching, right? The function they're touching is always the same function, no matter how much you slide it, either way. But here, we can pick either way. And so we're actually going to pick both ways so that we can see how to use the shell method and also how to do it with the wash method. And actually, I'm going to start with the shell method, which I know we haven't done yet, but I think we should. Okay. And yeah, that's easy. Are you crap? Or are you good? You're moderate. So here's what I have been saying. If you want to use the washer or the disk method, you have to make sure that your strip you draw is perpendicular to your axis of rotation. The shell method is not that. The shell method, in fact, I've always made the rhyme, shell means parallel. So if you know you want to use the shell method, or if you really it should be, if you end up drawing a strip that's parallel to your axis of rotation, you were forced to use the shell method. So I'm going to draw a strip that's parallel. Since I'm going around the y-axis, which is a vertical line, I'm going to draw a vertical strip. I'm going to rotate that around the y-axis. So here's what that ends up looking at. Here's what that ends up looking like. So if I rotate the strip around, I'm not going to get a washer. I mean, you could try to argue with the washer. You might have some. No, I don't like it. So I'm really just going to draw the strip, rotate it around. So I'm going to get is this cylindrical shell. So, right, like here is my strip, my rectangular strip. It's rotating all the way around the y-axis and giving me not a whole cylinder. It's kind of like a pipe, right? Where the pipe definitely has some thickness, but there's this hole in the middle that like the water or whatever goes through. So that is a shell of a cylinder. That's why it's called the shell method, because it's a shell. And we want to find the volume of this shell. Well, the volume of a shell, I kind of like to think of it as, it's going to sound kind of silly, as a roll of paper towels. And I'm going to take one paper towel off the roll, kind of unwind it. So when I unwind it, here's what happens. So I cut it maybe right there, and I unwind it. And I get, it's not perfectly a rectangular, or a rectangle with some thickness, because technically, like one side is a little bit longer than the other side, right? Because the inner circumference is a little bit smaller than the outer circumference, but it's close enough. But the volume here, well, this thickness is dx, right? Just like this thickness here is dx. And this length here is the length of the circumference, which is 2 pi times the radius. And we'll have to talk about the radius in a second. And the height of this cylindrical shell is the height of this strip, which is like every other time, the height of the strip is the top function minus the bottom function. Or if it was a horizontal strip, it'd be the right function minus the left function. Which in this case is top minus bottom is 3x minus x squared. Okay, here's where people get a little caught up with the shell method. Before, with the disk and washer method, the radii that we were talking about actually were the functions, right? We're saying, oh, we're going to do this strip, this slice, which is a disk or a washer, and the radius is how far the function is from the axis of rotation. That's not what the radius is anymore, not for the shell method. So what you have to do, and I kind of should have said this a little bit ahead of time, you have to imagine, not imagine, this strip is at a distance of x from the y-axis. Excuse me. Right, and because we're going to let x vary between how far left and how far right this goes. So when x is, like 1, right, we're going to have the height of this is going to be 3 minus 1, which is 2. And when x is 1, the radius of this cylindrical shell, well, if x is 1, you're literally 1 away from the axis of rotation. So the radius is going to be 1. So the radius, if you're going around a normal axis, meaning around the y-axis or on the x-axis, if If you're going around the y-axis, the radius is x. If you're going around the x-axis and using the shell method, the radius is y. So it's 2 pi x. So the volume of our shell is 2 pi r h d whatever is appropriate, which in this particular case is 2 pi x times h times dx. So here's what I remember. The washer method, or the disk method, the integral is pi times your big radius squared minus your little radius squared. Whereas for the shell method, the integral is 2 pi times your radius, which is either x or y, times the height of your shell, which is one function minus the other, times d whatever. So there's definitely a difference. Okay, so that's the volume of this shell. But again, we have to then say, well, the shells can go from x equal to 0, where we get, and so this one is much harder to draw, like all the shells. But the idea here is, right, like I would have pen. I would have like a shell from this strip here that would go, would give me like, come on, give me like a tiny shell, like that. And then I have another strip over here, and they give me a bigger shell, which I'm going to have a hard time drawing. Sorry, this is where my drawing skills might fail. By might, I mean almost definitely will fail. Where I have a bigger shell that's around it. So, my shell's looking terrible. But essentially, right, each strip you go further for that gets you another shell, the concentric shell around the smaller one. So we're adding up all the shells. So we're going to get the total volume. I'm going to write total a little bit nicer. Is going to equal the integral of this mess from my shells go, well, my strips go as far left as 0 and as far right as 3. Most of the time we pull out this 2 pi in front. So I get 2 pi times the integral from 0 to 3 of x times this. Which probably run out of room. Sure, I can erase this picture. I'll draw it again on the other side. So that's going to end up being 2 pi times the integral from 0 to 3 of 3x squared minus x cubed dx. We integrate, we get 2 pi times the integral of 3x squared is just x cubed. The integral of x cubed is x to the 4th over 4 from 0 to 3, plug that in, get 2 pi times 3 to the 3rd minus 3 to the 4th over 4. And then minus 0 minus 0. And again, I'm trying to make life easy. I really don't want to calculate 27 minus 81/4. What I really want to do is I want to factor out 3 to the 3rd. I'm going to write this as, hey, that's 2 pi times 3 to the 3rd. If I factor out the 3 to the 3rd, I'm left with a 1. If I factor out the 3 to the 3rd, I'm left with a 3 over 4. 1 minus 3/4 is easy. That's 1/4. So I'm left with 2 times 27 times pi times 1/4. 2 cancels with the 4, gives me a 2. So I end up with 27 pi over 2. And unless I've made some dumb mistake, which is possible, this should be the same as if we do it using the washer method. So let's do it using the washer method. Okay. Makes a cool sound. I feel like that's like a, sounds kind of like the Millennium Falcon is like ramping up to, or it's kind of like when the Millennium Falcon's like gonna ramp up to go to hyperspace, but then like doesn't have enough juice. It's like whoa, 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 whoa. It's kind of what it sounds like when I move my board over. Get all sorts of gems for me today. So like, yes, the teacher is not funny. It's all right. So, oh yeah, I think it's the same problem. So same region. All right, looks like this. This is y equals x squared. This is y equals 3x. And now we're going to use the washer method. Going around the y-axis, so that means we have to use a horizontal strip. So here's my horizontal strip. I go around the y-axis, and my horizontal strip. Yeah, sure. Right, there's my washer, for better or for worse. It's got a thickness of dx. It's got an area of pi times your large radius squared. That's the big circle. Minus pi times your little radius squared. That's the little circle that isn't there. Do be careful. You have to square each radii before you subtract things. So I definitely saw a couple people somewhere subtract things and then square the quantity after you subtracted. We have to square each thing first and then subtract them after that. So the volume of my washer is pi times r squared minus little r squared dx, where the big radius is the function that's further from the axis of rotation. So thinking about this, that's my larger radius. That's my smaller radius. But since things are, ooh, I made a small error. I made a mistake, and you guys are letting me get away with a lot of stuff today. I feel like maybe you're like, I don't really need to catch James. He's going to be just fine. I'm not. I make mistakes. It happens. My mistake here is I used dx when I should have definitely been using dy. Why? Makes me think of an old thing. Makes me think of the Mickey Mouse. Why? Because I love you. Why? Because it's a horizontal strip and it's got a small thickness that's in terms of y. So that should really be dy. That should also be dy. So I was about to ask, how do we need to write our functions? And we need to write them in terms of y because we have a dy. So this y plus 3x is actually x equals y over 3. And this y equals x squared is actually x equals to plus or minus the square root of y. Oh, which is it? Is it the positive square root of y or is it the negative square root of y? And it does matter. And you like that cricket sound effect. Cricket, cricket, cricket. Yeah, it's positive. Thank you. Appreciate the response. But I want to point out, right, usually we kind of default to just using the positive square root because that's kind of where we're usually at. But if someone gives you something like, if I gave you instead of the region on the other side, you would need to use the negative square root of y. So just be careful if that ever happens. So this is going to be pi times big R squared, which is the square root of y squared, minus little r squared, which is y over 3 squared dy. And then we're going to get the total volume by integrating. Do be careful. I've definitely seen people use the same limits integration when they shouldn't. So before, failed to go to hyperspace, light speed, whatever, I forget what they call them in Star Wars. It's okay. So in the previous one, our limits were x equals 0 to x equals 3. In this one, we're not going from left to right. We're going from bottom to top. So our limits are as low as this can slide, which is 0, and as high as this can slide, which is to y equals 9, because this point of intersection was the point 3, 9. So the total volume is going to be the integral from 0 to 9 of pi, with the pi in front, times this squared minus this squared. And I'm going to simplify a little bit. So square root of y squared is y. Y over 3 squared is y squared over 9. And then we're going to do the math. So we're going to get y squared over 2 minus y cubed over 3 times 9 is 27. Don't forget the pi. I often forget the pi, which is a shame because pi is delicious. Feeling a little loopy today, I gotta say. I don't know why. Just feeling like, yeah, let's make some silly, not that funny, but funny jokes. From 0 to 9. So plug in the 9. You get 9 squared, which is 81 over 2. Minus plug in the 9 here, and I'm just gonna write 9 cubed over 27. Plug in the zeros, you get zeros. I do want to remind you, I know it happens a lot of the time that when you plug in the zeros, you get zeros. You don't always get zeros when you plug in the zeros. So make sure you are mentally checking. Like if I plug in that zero, do I really get zero? Oh yeah, for sure. 0 squared is 0, 0 cubed is 0. 9 cubed over 27, I can definitely cancel one of those 9s and get 9 squared over 3. And then look what I've got. In case you hadn't noticed, I'm a big fan of this kind of trick. I've got pi times 81 over 2 minus 81 over 3. Yes, I could get a common denominator. I can multiply this by 3 over 3 and this by 2 over 2. But I don't want to. I want to factor out an 81 because it is easier. I get 81 pi times 1/2 minus 1/3. 1/2 minus 1/3 is super simple. That's 81 pi times 1/2 is 3/6. 1/3 is 2/6, right? I don't have to think about the common denominator. I'm just like, oh, well, times this by 3 over 3 times this by 2 over 2. It's really easy. Multiplying this by 3 over 3 is more mental energy I don't want to spend. So 3/6 minus 2/6 is 1/6. So I get 81 pi times 1/6, or 81 pi over 6. And canceling a 3, I get 27 pi over 2, which is the same answer we got on the other side. So we're happy. They're the same, as they should be. It shouldn't matter which method you use if you're being asked to calculate a thing, whether you do it the washer or the shell method, you should still come out to the same answer. Whew. All right, let's do another shell method problem. Let's see what have I got here. Oh, I've got a million cracks in my neck. Let's see, where did you go? Problem 1 to do, and then we'll do that. Yeah, we'll do another shell method, then we'll start talking about some arc length. Yeah, let's do that problem. Which I know we've looked at this region before. It's kind of one of my favorite regions. But we have, well, actually, we didn't look at this region before. We looked at the region right next to it. Okay. Hopefully you guys are hanging in the wind. Break. My friend was saying she takes breaks in around half one classes, and I was like, oh, maybe I should, but I usually don't need a break. But if you guys need a break, you can always take a break. I guess if you want to take a break, you can just take a break. And then you can always watch the video later. No breaks. Okay. Also, while I'm thinking about other things, vote. I voted yesterday, turned the ballot. It was great. It counted. If you are able to vote and you live in this country, I strongly encourage all of you to please vote. It is very important. Yeah, that's all I'll say. Vote, 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 vote. Vote, 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 vote. All right. So on to this problem. I want to find the volume. Maybe we'll just set up the integral. Maybe we'll actually find the volume. Or maybe we'll do it. Yeah, I see. So on the volume, solid, generated by revolving the region. One time I tried to make an acronym for this. I was like, you know, the VOSGVRTR. It did not catch on. Region bounded by x equals 0, y equals the square root of x, and y equals 6 minus x around the y-axis. Okay, that's what we're trying to do. And although it's not required, it is almost always a good idea to draw these. Now you can definitely use Desmos to draw these. I think it's a fine tool to use. Let's draw it. So I've got y equals the square root of x, which looks like our usual square root of x. I've got y equals 6 minus x, which is a line. Instead of y intercept at 6, it's got an x intercept at 6. So it looks like this. And then x equals 0 is this line here. So I'm looking at this region, not this region here. So it's really, really important that it can be easy when you've got like two regions that are both next to an axis to accidentally pick the wrong one. So if you're not sure, you have to make sure that all of the things that they're saying should be a boundary are actually boundaries. This region here, y equals 6 minus x is a boundary. y equals to the square root of x is a boundary, and the y-axis, which is the line x equal to 0, is a boundary. This line, y equal to 0, is not a boundary, so this shouldn't be a region. Okay, and I'm going to erase the rest of this. We don't really need it. What I do probably need, maybe, I don't know, yeah. I need this point. I need to know where these intersect. So you can totally set them equal to each other. And one way, the way I'm not going to do it, would be to square both sides and get a quadratic and solve for x. Easy way, which I know we talked about the other time I looked at a region like this, is to just guess. And now, I do not recommend this for your web work problems because usually they have garbage numbers. But for any problem that a human being has written for you, they will often try to make it so the numbers are not awful. That is certainly the case here. I'm going to guess easy numbers take the square root of, like 0. It's definitely not 0 because 0 doesn't equal 6. Or 1. Square root of 1 is 1, 6 minus 1 is 5. Or I'm going to skip the one that's the answer 9. The square root of 9 is 3. Oh, wait. What? Oh, no, that's not right. Square root of 9 is 3, 6 minus 9 is negative 3. Although I will tell you, if you drew the other half of y equals the square root of x, like if you drew doing this, these would totally intersect when x was 9, y is negative 3. But the point we're actually looking for is when x is 4. Because when x is 4, square root of 4 is 2, 6 minus 4 is 2. Okay. So I want to find the volume of this revolved around the y-axis. And although we could certainly use any method we want, right? I could for sure use it would actually be the disk method here, not the washer method, because my region is flush with the axis of rotation. So if I drew a horizontal strip, right, there isn't any inner radius to subtract off. The problem with the disk method here is you have to do 2 different intervals, right? The volume using the disk method would be, I got all these green pens, be the integral from 0 to 2, right, because we're doing in terms of y, of my radius of pi times the radius squared. And the radius here in this region is y to the square root of x, which is x equal to y squared. Plus, then you have to do the integral from the region from here to here. So that would be the integral from 2 to 6 of pi times my radius squared. Where my radius here is, if I solve this for x, it's actually the same. It's x equal to 6 minus 1. And this is perfectly doable, right? It's not like fun, but these are perfectly reasonable integrals to integrate and get an answer for. But instead, what we really prefer to do, we would prefer to use the shell method. Or I should say more generally, most people, trying to pick my less good pen, would prefer to use the method where they don't have to do 1 integral instead of 2. It's just less calculation. So I'm going to draw a vertical strip, because my strip has to be parallel to the axis of rotation. I know both my examples, I've been going around the y-axis, but if I was going around the x-axis, I'd be drawing a horizontal strip if I want to use the shell method. So I really want to emphasize shell, parallel. They kind of rhyme. They do rhyme. Whereas disk or washer method is perpendicular. They do not rhyme there. You could say the washer and vicular perpendicular. No, that's idiotic. Don't say that. So right, I'm going around the y-axis, and my shell is going to look like a very it's going to look very pipery. I'm going to have a shell. It's very tall. I'm going to draw that dash. Oh, well, it's not important. And again, you don't have to draw these pictures. I'm just trying to show you stuff, right? So that's why I have drawn pictures. So the volume of this shell, again, the volume of the shell is 2 pi r h d x in this case. Where the radius is just x, or whatever variable you're working with. Again, if you're going around a different axis of rotation, it's a little different. So here the radius is x. And the height is the top function minus the bottom function. So this would be 2 pi x times the height, which is 6 minus x minus the square root of x dx. And then the total volume would be the integral. That's not the pen I wanted. My good pen go. Sorry, I'm trying to keep track of the good pens. I think this is it. Feels warm. I can use it a little bit. The volume here is going to be the integral from, well, in fact, just with the 2 pi out in front. It's going to be 2 pi times the integral from 0 to 4, because now they're x values, not 0 to 2 to the 6 for y values, of x times 6 minus x minus, I would write that as x to the 1/2. Important point. You have to multiply that x through before you can integrate this. Just like here, you have to square these out before you can integrate them. Right? We only really are, I mean, I guess you don't want to try to use substitution. That's not the right way to go. Most of these area, volume, whatever problems, most of them are usually integrated by just multiplying out the thing and getting the answer. So this is going to be 2 pi integral from 0 to 4, x times 6 minus x times x minus x times x to the 1/2, which is x to the 3/2. So then we get, so you can differentiate the 6. Oh, don't be late. Remember the 2 pi. Remember the 2 pi. Okay, 6x squared over 2, which is 3x squared, minus x cubed over 3, minus x to the 3/2 plus 1 is 5/2. Divided by 5/2 is like multiplying by 2/5. From 0 to 4. Wow. So again, I see that when I plug in the 0, everything's going to be 0, right? 0, 0, 0. I plug in the 4, and you get some numbers. Big surprise, numbers, right? Yeah. So I'm going to do something simplified. So 3 times 4 squared, which is 16, minus 4 cubed, which is 64, over 3, minus 2/5 times 4 to the 5/2. 4 to the 5/2 is 4 to the 1/2, which is 2, to the 5th, which is 2 to the 5th, which is 32. So the interval is 0 to 4. Of course, I erased it. I guess I have to draw it again. So the reason it's 0 to 4, it's a fair question, right, is it was this region here. That's the point 0, 6. That's the point 4, 2. That's the point 0, 0. And if we're using a vertical strip, we're thinking about how far left the strip can go, which is 0, and how far right the strip can go, which is 4. So if you're drawing a vertical strip, you're always thinking about how far left and right it can slide in the region. On the other hand, if you were drawing horizontal strips, that's when your limits of integration would be from 0 to 6, although we had to break it up, right? So with the horizontal strips, the limits were 0 to 2, and then 2 to 6. So hopefully that clarifies things. Basically, if you're integrating with respect to x, your limits of integration should be the x values. And the x values for this are, oh, we're starting as far left as x equals 0, and we're going as far right as x equals 4. It's kind of a little bit confusing sometimes because you've drawn this vertical strip where the top and bottom are kind of like the bounds, right? Those are like the top of your strip. That's what you're subtracting. But then you're talking about how far left or right the strip moves. It's always like that. If you draw a horizontal strip, your left and your right functions are the bounds, but then you're talking about how far up and down the horizontal strip can move. That's why I look at the d whatever. The dx is like, oh, my limits of integration should be x values. I have to think about how far left, because x is left and right, and far left and far right. Yeah. Hopefully that clarifies things. 4 to the 5/2, again, that's 2 to the 5th, which is 32. Okay, once again, I'm going to use one of my tricks and say that I've got 2 pi times 3 times 16 is 48. And here I've got a minus 64 thirds, and negative 2 fifths times 32 is a minus 64 fifths. So I can factor out minus 64. And we're left with a 1/3. And here I had a minus 2 fifths times 32, which is a minus 64 fifths. The factor out minus 64 I'm left with a positive 1/5. It's not quite as nice, but things are not good. Oops, I wrote 15th. I said, you guys like, I can't see that anywhere. So then, this is not going to be fun, but we're going to add this all together. 2 pi. I know my common denominator is going to be 15ths. So I'm going to multiply this by 15 over 15. Here's an easy way to multiply by 15. Multiply by 10, and then add half of that. So 48 times 10 is 480. Half of that is 240. 480 plus 240 is 720. That's 48 times 15. And then, oh, sorry, 720 over 15. I multiply by 15 over 15. And then this is going to be 64 times, this is 5/15, this is 3/15, that's going to be 8/15. So I end up with hopefully a positive number. Yeah, it's a positive number. 2 pi times 720 minus 8 times 64 is 512. How do I know that? Because it's the power of 2. And 64 is 2 to the 6th. 8 is 2 to the 3rd. 2 to the 6th times 2 to the 3rd is 2 to the 9th, which is 512. 2, 4, 8, 16, 32, 64, 128, 256, 512. So I end up with 2 pi times 720 minus 512 is 208 over 15, which is going to be 416 pi over 15. What a gross looking number. Ow. Yeah, not ow, but head on the hand. Okay. I wanted to spend not quite so much time talking about all this, but I didn't. But let's go ahead and the last 12-ish minutes we have here, talk about arc length a little bit. So arc length really comes down to remembering kind of one formula. It's really 3 formulas, but really one formula. And let me see. Let me look. Actually, let's see something in the book so I can use consistent notation with what the book does. One momento. Let's see. Arc length. Okay, they do it that way too. Seems done. Do they call? They don't even call it that. Whatever. I'm still going to call it that. Okay, fine. Okay. So here's the idea. I'm trying, and someone already asked about this now. Sorry, the other day I'm going to do the same kind of thing. So I'm trying to find the length of this curve, y equals f of x, between, let's say, A and B. What I'm going to do is I'm going to break it up into a lot of little arc lengths. So like from here to here, from here to here, right? Just like we do with, just like how we're trying to find area, we break it up into a bunch of rectangles. But now I'm breaking it into just a bunch of little lengths. And I'm going to look at this length here in particular. I'm going to look at this region. I'm going to kind of blow it up. So say if I look at that square, and that's that rectangle, and I've got some curvy part of my curve. I know that's very specific. Some curvy part of my curve. And here's the whole idea. Just like we can find the area under a curve, we use rectangles to estimate the area, and then we let the width of those rectangles get really, really small to estimate better and better and better. Here, well, I'm not going to use a rectangle to estimate area. I'm going to use a diagonal line to estimate the length of that curvy line. Because I know how to find the length of a diagonal line. I can really use the Pythagorean Theorem. So the idea here is that this is a small change in x, this is a small change in y. So this is dx, this is dy. And this thing here, which I usually like to call L, I like to call it ds, I don't know. Anyway, I like to call the change, so I like to call this ds personally. I can say that ds, the small change in the arc length, is approximately equal to L, where I can use the Pythagorean theorem to figure out what L is. So I say, well, look, L squared is dx. So let's see, do I want dx first or dy first? I want dx first. That doesn't really matter, but it kind of matters. There we go, Pythagorean theorem. Dx squared plus dy squared equals L squared. I'm going to square root both sides, no big deal. But then I'm also going to divide both sides. Oh, actually, I'm not removing that. Sorry, take that back. I'm going to also divide this side by dx and multiply this side by dx. But dx I can rewrite as the square root of dx squared. And then a square root over a square root, I can make one big square root. So I can rewrite L as the square root of dx squared over dx squared plus dy squared over dx squared dx. Or dx squared over dx squared is 1. Dy squared over dx squared is dy over dx quantity squared, or the derivative squared. So they end up getting that L is the square root of 1 plus dy dx quantity squared dx. Or if you prefer the more functional notation, you can say that L is the square root of 1 plus f prime of x squared dx. You can also do it in terms of y. It's the same sort of deal. You can also say that L is equal to the square root of 1 plus dx dy squared, which is the derivative of x as a function of y, dy, or you could write it as the square root of 1 plus g prime of y squared dy. Okay. So that is the arc, that's the formula for ds, and then the whole length is just the integral of ds. So, right, I'm going to add up all the lengths by integrating. So here is what I really remember. And I remember this because we're also going to use the same idea when we talk about surface area in the next section. We're just going to add a little bit. If I'm trying to find arc length is the integral of ds, where ds is either one of these, depending on how your function's written. There's another version of this when we get to chapter 11 using parametric equations, but that's not now. So I really want to do one example for you guys because there's kind of two different things that happen. So let's say I want to find the arc length, and then, right, this is the integral of the square root of 1 plus your derivative squared d whatever makes sense. Okay. So I want to find the arc length of, sorry, I actually need to think of an example. I'll use the one I did earlier. Y equal to, I'll change that a little bit, 3 natural log of x. Sorry, plus, no, minus. Sorry, I have to think about what this needs to be. Just one sec. 1/24 x squared. From x equals 1 to x equals 2. And I'm going to give you a little preview here. I haven't done the integral yet, right? I've just made up the question. But I know what the answer is going to be. Because problems like this specifically, and this is definitely a certain type of problem, they're not all going to be like this, but this is one type you'll see a lot of. We'll talk more about other types on Thursday. Problems like this, well, here's the answer. At least the beginning of the answer. The beginning of the answer is going to be 3 natural log of x plus 1/24 x squared, evaluated from 1 to 2. That's right. it's going to be essentially the function I started with, except the sign in the middle is going to change from what it was to the opposite of that. Sometimes it changes from negative to positive, sometimes it changes from positive to negative. Now, why would this happen? Well, there's a whole process. So, let me just double check real quick to make sure I'm not making a stupid mistake. No, that should be right. Yeah. So, here's what's going to happen. Well, let's just do it. So, again, the arc length is going to be the integral of the square root of 1 plus the derivative. So let's write the derivative. The derivative is 3 times 1 over x minus 1 over 24 times 2x squared. Yes. Let's simplify that just a little bit before we multiply it. So it's going to be the integral of the square root of 1 plus 3 over x minus 2x over 24 is x 12 squared. Yes. All right, here's what's going to happen with a lot of these problems. You're going to square this out. And this is 3 over x minus x over 12 squared. And what's going to happen when you square this out is your middle term is going to be negative 1/2 all the time. Maybe not all the time, but for a lot of these problems it is. Why is that important? We'll watch. I know we got 3 minutes, so I'm going to do the work over here. So 3 over x, that's not my good rate of time. Crap. 3 over x minus x over 12 squared. So when you square this out, it's equal to the first thing squared. So it's going to be 9 over x squared plus 2 times the first thing times the second thing. Plus the second thing squared, which is going to be x squared over 144. But look, the middle term is negative 1/2. The x's cancel. 2 times 3 is 6, times negative 112 is negative 1/2. And I'm going to tell you repeatedly, that's going to happen a lot. It's going to happen especially if it looks like your original thing you're starting with is some function plus or minus some other function. Not always, but a lot of the time. Especially if when you take the derivative, you get powers that are opposite sides of each other. Right? 3 over x is 3 times x to the negative first, and this is x to the first. Those powers are going to cancel each other out when you multiply the squaring out, and you're going to get an x to the 0 in the middle. Now check this out. I'm going to add 1 to that. Well, if you add 1 to negative 1/2, what do you get? Sorry. So, in fact, yeah, I should take another screenshot here. Hopefully, if I ever don't take your attendance and you were here, just tell me you were. I will believe you. But I really want to finish this problem. So when you add 1 to negative 1/2, what do you get? I know it sounds like a dumb question, but I would like an answer. Thanks. But here's the thing. So if you add 1 to that, and I'm kind of out of room. Yeah, so I'm going to erase this. So if you add 1, here's what you're going to get. You're going to get 9 over x squared plus 1/2 plus x squared over 144. And here's the thing, that exactly factors back like it was before, except the sign in the middle has changed. This is exactly equal to 3 over x plus x over 112, sorry, x over 12 squared. I really want everyone to see this because it is a vital thing to see. If you see that when you multiply this out, the middle term is negative 1/2. And then you add 1 to that, the middle term changes signs, and then it refactors back to the way it was before, except the middle sign changes. Well, that's really great, because then look, we can write this. Sorry, I forgot my limits of integration here. We can write this as the integral from 1 to 2 of the square root of 3 over x plus x over 12 squared. Well, I know what the square root of something squared is. It's just that something. So this ends up being the integral from 1 to 2 of 3 over x plus x over 12. And I definitely know how to integrate 3 over x plus x over 12 because I definitely got the 3 over x and the x over 12 by differentiating this. So the integral of 3 over x is 3 natural log of the absolute value of x. And again, I'm a little running out of room here. This is going to be 3 times the natural log of the absolute value of x. And the integral of x over 12 is x squared over 24. From 1 to 2. Hey, look, I called it. I mean, I knew what the answer was going to be because, like, I know how this works. But this happens a lot. You do this whole kind of process and you get back to essentially the function you started with, except the sign in the middle is changed. And then you plug in your limits of integration. So if we plug in our limits of integration to finish things off, we end up with 3 natural log of 2. I'm not writing the absolute value of 2 because the absolute value of 2 is 2. Plus 2 squared over 24 minus 3 natural log of 1 plus 1 squared over 24. Natural log of 1 is 0. This ends up being 3 natural log of 2. 4 minus 1 is 3 24ths, which is 1/8. But I really, really, really want to stress for you all. This type of setup, when you see, oh, y is like some function of x minus some other function of x, and you kind of got powers of x, or things with the derivatives will be powers that are opposite signs. One is positive something, one is negative something. Almost always work out this way, where you take the derivative, you square it, the middle term is negative 1/2, you add 1 to it, the middle term is positive 1/2, you factor it back out, you take the square root of that, you start with, and you get back to the function you started with, except the middle sign has changed. You still have to show the work. So you can't just do this and be like, oh, it's going to be that. Even though I did that in the beginning, you actually have to show all things. But a lot of these problems work out this way.